Welcome to Klein's Calculus. Today we are going to be looking at deriving the law of exponential change using separation of variables and using the law of exponential change and the formula for compounding interest to answer real world questions. We're going to start with the idea that anytime we have a change, that change is proportional to the amount present. So we can say the change equals a constant in proportion times whatever we're starting with, or whatever's changing, excuse me. So if we use separation of variables, we can take and solve this equation, finding the antiderivative. We need to start by getting our y's on the left and multiplying by dt. Then we're going to take the antidifferentiate both sides. And recall that the antiderivative of y to the negative 1, or 1 over y, is the natural log of y. And the antiderivative of a constant is that constant times the variable of integration. And then we throw on plus c. Now when we're dealing with the natural log, we've got to remember that the natural log can't be a negative number. So we're going to have the absolute value symbols about it. So now, to solve this further, because we're going to find a function here, we're not going to be able to plug in a point and find c. What we're going to do is we're going to raise both sides with base e. And this will cancel out, and I have the absolute value of y equals e to the kt plus c. Recall that from our rules of exponents, I can call that e to the kt times e to the c power. Now, if I think about this, I need to solve this for y, not the absolute value of y. So, e to some power is going to be a constant. So, I'm just going to put that in front of e to the kt power, which is going to contain a variable. And to get rid of my absolute value signs, I just put plus or minus there, because that's my definition of absolute value. It could be positive or negative, and it's going to come out positive. Now I'm going to do one more trick just to make this a formula that we can deal with. This value is going to be the initial value of the quantity that's changing. So we're going to call it y initial, y sub 0. So right here is the antiderivative of this proportional function. And that is our law of exponential change. Okay? And in all exponential growth problems, that rate of change is proportional to the amount present. That's why we could say dy dt equals k, constant of proportion, times y. And you know that the faster, more bacteria in a dish, the faster the population is going to grow. You may know that the more radioactive material is present, the faster it's going to decay. And the differential equation to describe that growth will always be this function that we started with and this solution, the antiderivative, that we will use when we're solving problems. And if k, this proportional constant, this constant of proportion, is positive, well, that's going to grow. If it's negative, you think about it as 1 over e to the kt, and it's going to decay. And y initial, remember, this is always going to be the amount you start with. So let's see how this works, okay? So let's apply this law of exponential change. First things you're going to be able to do, and this is just going to be some very simple problems on your homework, is you might get something that looks like this. Hey, find the solution to the differential equation dy dt equals ky. K is a constant, and it satisfies given conditions. Well, you know the solution to this equation is this equation. So all you need to do is write this equation. And they told you k was 1.5. So you're going to put 1.5 in place of k. And they told you y initial at time 0, y is 100. So that's going to go in place of this. So y equals 100 e to the 1.5 times t. And that's the solution. It's another equation, but it's one we could use to find at any time t, how much stuff do we have, okay? You might also get some problems like this where they don't tell you k, but they do give you 2 points. Well, the one thing you always want to look for is y initial, when t equals 0. And in this case, it's 50. So if I was going to look at y equals y initial times e to the kt, I can right away put in 50 here. But I have to find t yet. Way to find t. Take your point. They gave you another point here. So I know y initial. I know it's 50. And I've got this point where this is t and this is y. So I can put in 100 for y. I've got my y initial. And I can put in 5 for t. And if I do that, I can solve that for k. Well, divide by 50 and then take the natural log of both sides and divide by 5 to get k alone. So this is k. Little algebra and you're there. But you do need to know y initial and a point. Okay? Once I've done that, you can look at k as the natural log of 2 over 5 and put it in this way. You can put it with a t next to it. Or in some cases, you'll see people, if k gets too complex, just rounding it. But if you round it in your homework, make sure you store it in your calculator when you're finding values. Okay? Now, we're going to compare that continuous change with the formula for compounding interest, you know, where we compound it just every year or every 6 months, not as often as that continuously compounding that we just looked at. And I just want to review that with you because we haven't seen this since chapter 1. Recall that the formula for compounding interest, if you're doing it at finite periods, the amount you have at any time equals the initial amount times 1 plus the interest rate divided by the number of times you compound per year. And that's all going to be raised to the number of times compounded per year times t, and t is in years. So freeze the slide, write it down if you still need this. Okay, so now let's look at, okay, if we compound it continuously, then the limit as k approaches infinity of this function that we just looked at is the initial amount times e to the rt, which is very similar to when we said y equals y initial times e to the kt. Notice it's the same thing. You're looking at an exponential growth, okay? So when you see this, and we looked at this and we used this in chapter 1, it's the same exact thing as what we just did when we derived that law of exponential change. Same thing. The amount you start with, whether it's money, bacteria, radioactive substance, whatever, the change, the growth change, could be interest rate, could be any other kind of growth change, in time and years. So, same formula, don't get confused by it. Okay, let's look at it with money first, then we'll move on to other things. Suppose you deposit $800 into an account that pays 6.3% annual interest. Let's look at how much we're going to have 8 years later if the interest is compounded continuously or quarterly. If you look at compounded continuously, we use this formula. So I would just say my amount at 8 years is the initial amount, $800, times E, my interest rate, make sure you change that to a decimal, 0.063. And my time is in years, so I'm going to have times 8. So I multiply that all out, and I do not do this ahead of time, which I should have. So I've got 800 times e to the, and in parentheses I'm going to put, 0.063 times 8. Make sure you got your whole interest rate. So I'm going to have $1,324.26. This is one of the few times we don't round to the thousandths place, folks. It doesn't make any sense. Money rounds to the hundredths place. Now, if we compound quarterly, we're going to use this function for quarterly. And k is going to equal 4 times a year. So now I've got, after 8 years, I'm going to have my $800 times 1 plus my interest rate divided by 4. And I'm going to raise that to the 4 times 8 power. Okay? So once again, we come over here, and now I've got a little different formula. I shouldn't make as much money because they're not compounding my interest as much. So 800 times 1 plus 0.063 divided by 4. And I'm going to raise that to the, I'm just going to say 4 times 8 is 32. And notice, I didn't make as much money. Almost $5 less. So, it doesn't seem like a huge deal, but still, a buck's a buck. So, $1,319.07. So, a little less money. You expect less money if you compound over a finite time as opposed to compounding continuously. That's going to give you your best deal. Now, let's talk about using this exponential growth in other forms. When an atom, radioactivity, when an atom emits some of its mass as radiation, the remainder of the atom forms a new element. This process is called radioactive decay, and when the elements are doing it, they're radioactive, not so good for you. An example is radioactive carbon-14 turns into nitrogen, the radium turns into lead, some examples. And experiments have shown that at any given time, the rate the radioactive element decays is proportional to the number of radioactive nuclei present. So we can use that law of exponential change because it's proportional. So the decay is described by our equation, dy dt equals ky. And if it's decay, k is going to be less than 0. If it's growth, it'd be more. If y initial is the number present, we can use the solution here, y equals y initial times e to the kt, to find out what we have left at any time. Okay? And the half-life of the element is the time required for half of the nuclei present to decay. So that'll come up as a base further after on tomorrow's lesson, I believe. Okay? Oh, it's going to come up right now. Sorry. Find the half-life of a radioactive substance.
Staff and students, again, apologize for the interruption. Please remain in your